students. Good morning all of you, ma. How are you all? Right, you are doing great. So students, today in this class I am going to start a new topic. So last class we have learned interpretation of deviation and also critical phenomenon. Right students? So hope you have noted down all the points in your notebook. Fine. So today a very interesting topic. So students, are you ready for the class? Okay. So kindly put the side heading, students. ANDREWS isotherms of carbon dioxide. Today's topic, students, in this class we are going to learn ANDREWS isotherms of carbon dioxide. Okay. So please put the side heading. Okay. Now, so you might be knowing what an isotherm is. What is an isotherm, students? It's nothing but, so the main point which comes into your mind immediately after looking at this word isotherm is constant temperature, right? So here what are these ANDREWS isotherms? These are the curves, students, which explain the relationship between pressure and volume at constant temperature are called as isotherms. Okay, so this is the common definition of isotherm. What is an isotherm, students? It explains the relationship between pressure and volume at constant temperature. Okay. So keep this isotherm aside. Then what are these ANDREWS isotherms of carbon dioxide? So Andrew, name of a person. That means he has studied the behavior of carbon dioxide. So what all he studied, now I am going to let you know. Okay. So Andrew, what he did was, students, he studied the effect of pressure on volume of carbon dioxide at different constant temperatures. So what did he do, students? He studied, or he noticed, or he observed the influence or effect of pressure on volume of carbon dioxide at different constant temperatures. Okay. So he has selected one temperature. There what he did, he has changed the pressure value and he observed how the volume of carbon dioxide is being changed. Okay. So that means, students, he measured the volume of carbon dioxide at different pressures, keeping the temperature constant. Okay. For example, 10 degrees centigrade. Okay. So he has taken some pressure and he exerted this much of pressure on carbon dioxide. So how was the volume of carbon dioxide at this temperature? 10 degrees centigrade. He changed the value of pressure, checked the volume of carbon dioxide. 10 degrees centigrade, he changed the value of pressure, he checked the volume of carbon dioxide. So now he has now he is loaded with the values of pressure, volume and various constant temperatures. Okay, students. So whenever a person is doing an experiment, so what he does with the values obtained, with the set of data, what he does is, he will take a paper, a pen, immediately he will plot a graph between the two factors. Okay, students, then he will come to know what is happening at this pressure, what is happening at this temperature. Okay, so the same here Andrew has studied about the volume of carbon dioxide changing the value of pressure at various constant temperatures. Okay, So after getting few values, what he did, he plotted a graph between pressure and volume at different constant temperatures, from which he could obtain various isotherms. Okay, so from these isotherms he could give us the information, a lot of information about carbon dioxide. Are you ready to look at the isotherm, students? Okay, so we also will plot a graph between pressure and volume at different constant temperatures. Take a pencil, scale, eraser. Ready? So this is the graph plotted by Andrew between pressure and volume at various constant temperatures. Okay, students? So draw this graph and these are the isotherms shown here. Okay, carefully draw this graph. X-axis volume is taken, y-axis pressure is taken. Okay, so mark here point A, temperature 13.1 degrees centigrade. Okay, next point B, here point C, here point D. Okay, so the first isotherm is named as ABCD. Fine. Second isotherm at 21.5 degrees centigrade, point E, F, G, H. Okay. Next third isotherm at 31.1 degrees centigrade. This point name it as X. Okay. Next isotherm 41.8 degrees centigrade. Just draw a steep line, a continuous curve. Next. Okay, students, here this portion you mention it as liquid. Okay, here gas plus liquid. So draw the diagram carefully, students. So when you are asked the question, Andrews isotherms of carbon dioxide, first you should write the definition of isotherm. What is it, students? The curves which explain the relationship between pressure and volume at constant temperature. Next, Andrew has studied the effect of pressure on volume of carbon dioxide at different constant temperatures. Okay, so from that he measured the volume of carbon dioxide at different pressures at various constant temperatures. Then he plotted a graph between pressure and volume at different constant temperatures, from which he could obtain various isotherms. So below you should draw this graph. The graph should be very neat, students. Looking at the graph only, even if the theoretical part is correct, if the graph is wrong, you will lose your marks. Why? Because if you know this graph, easily you can write the points once you understand the graphical representation. Okay, now let us learn the isotherms one after the other, students. Okay, so first isotherm, students. So what all temperatures Andrew has mentioned in his experiment. Look at the diagram in your notebook. Okay, on the board now I made it small, students. Look at the diagram in your notebooks. So what are the temperatures that he has taken? First one 13.1, next 21.5, third one 31.1. Okay, so these are the three isotherms which gives us the complete idea of the behavior of carbon dioxide, that is how pressure is influencing volume of carbon dioxide at various constant temperatures. So we'll start with the first isotherm, which is taken at the lowest temperature. What is the lowest temperature mentioned here, students? That is 13.1 degrees centigrade. So our first side heading goes like this: isotherm at 13.1 degrees centigrade. Okay, students? So put the side heading isotherm at 13.1 degrees centigrade. So look at the isotherm, it is named as ABCD, students. What is the name of this? So don't write what I am writing now. So it is named as ABCD. Okay. So point A, what you should understand here. So point A, volume. Students, this is the origin point. Okay. As you all know, from here to this side, volume is increasing. From here to up, pressure is increasing. Okay. So almost here, the volume will be maximum. Okay. And pressure corresponding to this point, pressure value is very low. Okay. So at low pressures, volume is too high, means carbon dioxide. What might be its state, students? Yes, it exists as a gas at point A at low pressures and also at the lowest temperature 13.1 degrees centigrade. Okay, so the same I have written here. Write down in your notebooks also. This isotherm at lowest temperature, brackets, mention it as 13.1 degrees centigrade. 13.1 degrees centigrade, close the bracket, students, exists as a gas. Okay, exists as a gas. Wait, now we are coming back, we are going up. Andrew is studying the effect of pressure. So slowly what he did, at the same temperature, what is the temperature? 13.1 only. Now he is slowly increasing the pressure value. So when he is increasing the pressure, what happens, students? Look at here. This curve is slowly coming back. It's not going that way or it's not going up. Okay. So it is coming back. It is coming back means what is happening to the value of volume? Volume is being decreased. Okay. So pressure is increasing. Volume of carbon dioxide is decreasing. So that's what I mentioned here. So this isotherm at lowest temperature at low pressures exists as a gas, and here comes and, students, and as pressure increases, what's happening, students? Volume of carbon dioxide decreases. Volume of carbon dioxide decreases. This is a common concept. We all know that when pressure increases, volume automatically decreases. Why? Because these two are inversely proportional. We know this, right, students? Okay. So as pressure increases, volume of carbon dioxide decreases. As we named it, you can write decreases along AB. Okay, so this is what you should write under the first isotherm, which is at 13.1 degrees centigrade. Okay, students, have you all written? Once again, I am repeating. Please, under isotherm at 13.1, the isotherm at lowest temperature, brackets 13.1 degrees centigrade, at low pressures exists as a gas, and as pressure increases, volume of carbon dioxide decreases along AB. Okay, that is about part AB. Okay, now BC is there, CD is also there. It is a single isotherm, right? Okay, so till point B you understood. Now what happens at point B, students? At point B, what happens? Students, pressure is increasing. The molecules of gas are coming close to one another. Slowly what happens? The state from gas starts converting into liquid. Very good. Okay. So the molecules will be coming close to one another. Therefore, we say at point B, what happens, students? Liquefaction begins. Okay. So first portion AB you understood. Next BC I am explaining now. Okay. At point B, liquefaction begins. What is meant by liquefaction, students? Conversion into liquid. Okay. You understood now why it is converting into liquid? Because pressure value is increased. Okay. So at point B, liquefaction begins. And you can observe in the figure, students. Just observe the portion BC. How it is? B is here, C is here. A horizontal line is there. Okay. So the value of volume is here at point B and the value of volume at point C is here. Okay. So from B to C, what happened? Volume suddenly decreased, students. Okay. So it started converting into liquid. Immediately the volume of the gas suddenly decreased along BC at the same pressure. Okay. So that's why we can see a straight line here, students. Fine. So at point B, liquefaction begins and the volume of the gas suddenly decreases from B to C. Okay. The volume of the gas suddenly decreases, and what might be the reason for this, students? What might be the reason? Because volume of a liquid is less when compared to volume of a gas. Okay. Therefore, immediately what happens? The volume suddenly decreases from point B to point C. Okay. So, what you should write in your notebook, I will tell you. Write down. Don't worry. At point B, liquefaction begins and there is a sudden decrease in volume. There is a sudden decrease in volume at the same pressure. At the same pressure, because volume of a liquid is less when compared to volume of a gas. Volume of a gas. Full stop. Next point, write down. The sudden decrease in volume of the gas is shown by the horizontal portion BC part of the isotherm. BC part, P-A-R-T. BC part or portion of the isotherm. Okay, students. Now, at point C, what happens? At point C, below write down. At point C, liquefaction is complete. What is the meaning? Liquefaction is complete means? By the time it reached here, point C, it is completely converted into liquid. Okay? And even if you increase pressure, what happens? It will have very much less effect on volume. Why, students? What is the reason? Because liquids are much less compressible when compared to a gas. Okay? So that's the reason, students. See a steep line CD you can observe after point C. Okay, got it, students? So write down here. At point C, liquefaction is complete and increase in pressure has less effect on volume. Okay, because liquids are much less compressible. Liquids are much less compressible when compared to gases. Full stop. Therefore, a steep line CD is obtained. A steep line CD is obtained. Full stop. Below write down, students, conclusion. Okay. So students, all these points you are supposed to write under the first isotherm at 13.1 degrees centigrade. So what will you write under conclusion? CO2 exists as a gas along AB Next, partially as a gas and liquid along BC and completely as a liquid along CD. Okay, so this is the conclusion under isotherm at 13.1 degrees centigrade. Students, you might not get the question explain Andrews isotherms of carbon dioxide. Sometimes what happens, they will ask you explain the isotherm at 13.1 degrees centigrade. Then you should be able to write all these points. What happened at point A? What happened at point B? What happened at point C? Okay, and at the end comes the conclusion. Okay, so all these points you are supposed to write under isotherm at 13.1 degrees centigrade. Next, above that, what is the next temperature, students? 21.5 degrees centigrade. Now put the side heading isotherm at 21.5 degrees centigrade. Students, I want to ask you a question. First isotherm, you completely understood. What is the name of the isotherm? ABCD. Okay. Now, next isotherm is at 21.5 degrees centigrade. It has also got a name and its name is EFGH. Okay. So, can you notice any difference between ABCD and EFGH? Look here. This is 13.1. This is 21.5. Okay. So, any difference between these two isotherms, students? Both are alike. Okay. Both are same, looking same like twins, right? But what is the difference? Can you notice the difference between these two? The same explanation, students, for this also. Same at point E, at point A, what you have written? Same point E, same point F, same point G and same point GH. Okay, so no need to explain this isotherm. Why? Because these two are almost same. But the only difference between these two is, look here students, this is point B, this is point F. So what did we learn about point B? At point B, what happened? Liquefaction begins. At point F, liquefaction begins. But the pressure value when compared to B, F pressure value will be little bit higher. And this horizontal portion where liquefaction takes place, okay, where the gas exists as partially as a gas and partially as a liquid, where sudden decrease in volume takes place, that is slightly shorter than this BC. Only those two you will mention under this isotherm, students. Okay. So will you write down the points here? Write down. This isotherm at 21.5 degrees centigrade, this isotherm at 21.5 degrees centigrade is almost same as 21 same as the isotherm at 13.1 degrees centigrade. 13.1 degrees centigrade. Full stop. But there is slight difference. There is slight difference between the two isotherms. Between the two isotherms. Below write down. A. Liquefaction begins at higher pressures. Liquefaction begins at higher pressures, and point B Point B, the horizontal portion FG, the horizontal portion FG, where liquefaction takes place, is slightly shorter than BC. Full stop. Okay. So this is quite easy for you students, right? But no one will ask you, write about the isotherm at 21.5 degrees centigrade. Even if they ask you isotherm at 21.5 degrees centigrade, you should be able to write all the points which we have written under 13.1. At E, it exists as a gas. As the pressure increases, volume decreases along EF. At F, liquefaction begins and there will be a sudden decrease in volume along FG because volume of the liquid is much less than the gas. And at G, liquefaction is complete. And even if you increase pressure to a higher extent, there will be less effect because volume of the liquid is, liquids are much less compressible. So if they ask you the most probably they don't ask you, they'll ask you at 13.1 only. But if they ask you, you should be able to write all these points under 21.5 degrees centigrade also students. Okay. So next comes the isotherm at 31.1 degrees centigrade. So isotherm at 31.1 degrees centigrade students. So this is also an important isotherm like 13.1 degrees centigrade. Okay. So carefully observe the isotherm at 31.1 degrees centigrade. So what happened to this isotherm students? Look here. Look at your diagram. Okay. The first isotherm 13.1. Next 21.5. Next is considered at 31.1. That means slowly the temperature is also being increased. So what happened is when temperature rises or is increased above 21.5 degrees centigrade, here all the isotherms were not shown for us in the diagram. What might have happened? Some temperature like 25 or 29, one isotherm must be like this. Some more higher temperature, one more isotherm. Next isotherm at higher temperature. Okay. So finally at 31.1 degrees centigrade, the isotherm is like this students. So what did you understand about this horizontal portion? Here liquefaction started. That means conversion of gas into liquid started. And here liquefaction is complete. So this portion, horizontal portion, we say that where liquefaction takes place. Okay. So when temperature is increasing slowly and slowly, what happened to this horizontal portion students? It has become slowly shorter and shorter as the temperature was increasing above 21.5 degrees centigrade. Understood now students that point? So write down here when temperature increases. Write down when temperature increases. When temperature increases above 21.5 degrees centigrade, above 21.5 degrees centigrade, comma, the horizontal portion becomes shorter, comma, shorter, comma, shorter, and finally, students look here. At this point, what happened now? We cannot see the horizontal portion. Horizontal portion is nothing but where we can find both the states, gaseous state as well as liquid state. But here what happened? By the time the temperature reached 31.1, what was the behavior of carbon dioxide? We cannot here make out the horizontal portion. That portion has become a single point, students. Okay, so that's what you will write. When temperature increases about 21.5 degrees centigrade, the horizontal portion becomes shorter, 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 and finally becomes a point X, name it, a point capital X at 31.1 degrees centigrade. At 31.1 degrees centigrade. Full stop. So what is this point X telling us, students? There is no horizontal portion seen at X, that is at 31.1 degrees centigrade. That means here we cannot distinguish liquid and vapor states of carbon dioxide. There is no distinction between liquid and vapor states of carbon dioxide. Okay, so that's what this point X tells us, students. Below write down. This point X tells us that there is no distinction between gaseous and liquid states of carbon dioxide. Gaseous and liquid states of the gas, and is called as students, last week I told you about critical phenomenon, boiling water in a closed container. What did I tell you there? Yes, that is critical phenomenon. Same here, the point at which there is no distinction between liquid and vapor states of the gas is said to be a critical point. Okay, so this point X tells us that there is no distinction between gaseous and liquid states of the gas and is called as critical point. Critical point. Write like this, students. Okay, critical point. Underline. Full stop. The gas at this state is said to be in critical state. The gas at this state is said to be in critical state. Full stop. The temperature, pressure, and volume corresponding to this point are called as what are they, students? Critical temperature, underline, critical pressure and critical volume. Full stop. Okay, understood now, students? Below that write down. See, we discussed about below you can mention one more point. So critical point is this, students. Above this we have mentioned the state of carbon dioxide as gas. So what does it mean? Above critical temperature, liquefaction cannot be done whatever extent you increase the pressure value. Okay, so below write down. Above 31.1 degrees centigrade, liquefaction of the gas is not possible. Whatever pressure is applied. Full stop. Okay, next. What is the portion remaining about which we haven't discussed or learned? What is that, students? See some dotted lines here, right? So how did we get this, ma? How did we get this? See, I will show you once. So the isotherms were like this, na? So this is critical point. So what did we do? We joined the ends of horizontal portions and also the critical point from which we could get a boundary like this. Okay? Fine. So below that you write down, students. Next point. By joining the ends E and DS, the ends of horizontal portions, by joining the ends of horizontal portions and the critical point, we get a boundary. We get a boundary, B-O-U-N-D-A-R-Y. We get a boundary inside which there exists gaseous and liquid states in equilibrium. Inside which there exists gaseous and liquid states in equilibrium with one another. That is the gaseous and liquid states can be distinguished from one another. That is, the gaseous and liquid states can be distinguished from one another. Full stop. Outside the boundary, comma, there exists one state, comma, either liquid or gas, and there is no distinction between liquid and gaseous states. There is no distinction between liquid and gaseous states, which is termed as continuity of states. Underline continuity of states. Full stop. Okay, students. Now you understood how did we get that? How we could get that boundary? How did we get the boundary? By joining the ends of the horizontal portions along with the critical point, we could get a boundary. So inside the boundary, we can find the two states in equilibrium. That means we can differentiate gaseous state and liquid state. Now outside the boundary, this side if you see there is liquid, this side if you see there is gas. That means there exists only one state. Okay, so you cannot differentiate gas from liquid here. You cannot differentiate liquid from gas here. So that is what we call it as continuity of states. Okay, students. So this is all about Andrews isotherms of carbon dioxide. Okay, so draw a line till here, students. So what did we learn under Andrews isotherms of carbon dioxide? Go back and fatafat I will repeat once again. Check it. First, you will define what an isotherm is. Next, what Andrews has done. What did he study? Later, he has drawn a graph. These are the isotherms. So, below that, we have learned isotherm at 13.1 degrees centigrade. So, portion AB. Next portion BC. Next portion CD. Okay. So all those points will come under isotherm at 13.1 degrees centigrade. Next comes isotherm at 21.5 degrees centigrade. The first and second isotherms are almost same, and mention the difference. What is between those two. Next isotherm at 31.1 degrees centigrade. So we have learned about critical point, critical state, critical temperature, critical pressure and critical volume, and finally what we did, continuity of states. Nothing but we cannot differentiate. That means here there is only liquid, no gaseous state. Here there is only gaseous state, no liquid. So if there are two states, we can differentiate. Okay. So which is termed as continuity of states. So what you do, students, now draw a line till here. Till here you are supposed to write the answer for Andrews isotherms of carbon dioxide. Next, students, this is a short answer question. Put the side heading critical constants. Put the side heading critical constant. These might be asked as 1 mark questions. Okay. So what are critical constants, students? TC, PC and VC. What are these TC, PC and VC? Critical temperature, critical pressure and critical volume are called as critical constants. Students, do you remember van der Waals constants? What are they? Small letters A and B. Very good. So, but these are critical constants. What are the students? TC, PC and VC are called as critical constants. Now, let us learn the definitions of all the 3 critical constants. First one, put the side heading critical temperature. Brackets TC. Critical temperature brackets TC. Write down. Underline, students, underline the side heading. The temperature above which a gas cannot be liquefied. The temperature above which a gas cannot be liquefied. Whatever pressure is applied, whatever pressure may be applied is called as critical temperature. Is called as critical temperature. Full stop. Example, students. TC of carbon dioxide. Just now we have learned what is critical temperature of carbon dioxide. 31.1 degrees centigrade. Write it as the example. TC of carbon dioxide 31.1 degrees centigrade. Okay. So this is close to room temperature, students. That is why Andrew has selected carbon dioxide as it is very much easy to study the behavior. Next, critical pressure brackets PC. The pressure required, write up, the pressure required to liquefy a gas. The pressure required to liquefy a gas at its critical temperature. At its critical temperature is called as critical pressure. Is called as critical pressure. Full stop. Example, PC of carbon dioxide. PC of carbon dioxide 72.9 atmospheres. 72.9 atmospheres. Next below, critical volume VC. Critical volume VC. The volume occupied by a gas. The volume occupied by a gas at its critical temperature and critical pressure. At its critical temperature and critical pressure is called as critical volume. Is called as critical volume. Full stop. Example, VC of carbon dioxide is 97.2 liters per mole. 97.2 liters per mole. Okay. So this doesn't come under Andrews isotherms of carbon dioxide, students. This is a separate short answer question. So like you will be asked the question, define TC, PC and VC. 1 mark, 3 marks question. Okay. So like that will be asked about critical constants. Okay, students. So this is all for today's class. So we have learned a very interesting and important essay question, Andrews isotherms of carbon dioxide, and a short answer question, that is critical constants. Please carefully write down all the points in your notebook, students, and also study well. Please don't neglect. Immediately after the class, complete learning the topic. Then it will be easy for you at the time of exams. Okay, students, stay safe, stay home and take care. Bye-bye.